Modern amateur radio equipment often has the option of remote control over a data link. Indeed, some don't have any physical controls like knobs, switches or buttons at all, and can only be operated in this way. I've got two devices where this applies, a software-defined receiver or SDR and a digital transceiver. I decided to remotely locate them away from the operating position at the bottom of the garden. This means they are close to their antennas with no need to use long runs of coax to get the RF into the house. The remote location also means the antennas pick up less of the inevitable radio noise in typical urban settings from electrical, electronic and telecoms equipment. However, remote location has two main problems. One is how to safely power the equipment, and secondly how to implement the necessary data link back to the operating position. Since both pieces of equipment are controlled over USB cables, which are specified to be a maximum length of 5 meters, some way of increasing this distance is necessary to reach my desired location. This video shows how I went about achieving this. Let's go through the system diagram bit by bit. Here are the two main players in my remote bottom of the garden system. There's a software-defined receiver, an SDR. This is an SDR Play RSPDX, which covers 1 kHz up to 2 GHz, offers 3 remotely selectable antenna inputs, and is powered from 5 volts DC over a USB connection. The other unit is a QRP Labs QDX digital transceiver. This works on 4 amateur HF bands, 80, 40, 30 and 20 meters, and operates with various digital modes such as FT8 and Whisper WSPR. Its output power is around 5 watts and it too is controlled over a USB link, although it does not use the 5 volt supply from the USB but is separately powered at 12 volts. Now let's look at the RF side of things. The SDR uses an active antenna for LF, MF and HF reception. This is powered from a nominal 12 volt supply which is injected onto the coax cable inner that carries the signals to the receiver. The injector consists of chokes and capacitors to isolate the DC supply from the RF signals on the coax. There's also a simple vertical VHF dipole provided for VHF reception, intended for use between approximately 120 to 150 MHz. Each antenna feed is fitted with an RF protection unit to limit the signal level to about 1 mW maximum, the specified limit for the SDR Play receiver. This consists of back-to-back Schottky diodes across the coax line with a small series resistor. The antenna connection of the QDX transceiver passes via a reflectometer, which measures the forward and reverse waves in the coax line to show how well the antenna is matched. The coax then feeds into a set of 4 antenna selection relays, which select the appropriate matching network for each of the 4 HF bands. The actual antenna is a sloping 11-meter wire fed against a ground radial system. Now we look at the way the units are controlled and how they pass their data to and from the PC. For this we use 2 boxes which form a USB extender. The PC USB lead plugs into the sending end of the extender, marked TX. This converts the USB signals into a suitable format to be carried on a 4-pair Cat5e cable. This is of outdoor quality and part of the run is buried in the ground. At the remote end, a box marked RX converts the signals on the Cat5e cable back to USB format. This box also acts as a 4-way USB hub, meaning there are 4 sockets to which USB leads can be connected. 2 of these are used for the SDR and QDX units. Note that the signals on the Cat5e cable are not in IP format as you would see on a typical LAN connection, but are specifically designed to carry the USB signals. In my case, the Cat5e cable can be up to 50 meters long between the TX and RX boxes. A common mode choke is installed on the Cat5e cable near where it leaves the PC. This consists of several turns of the 4-pair cable around ferrite toroids and is meant to inhibit radiation and conduction of spurious noise signals to the remote equipment. Now the power arrangements. For safety, all the remote equipment is powered from an LV switch mode power supply, which produces about 18 volts DC. This is a well-engineered Chinese-made unit from Meanwell, and is rated at 75 watts maximum output, although it's normally producing much less, peaking from around 25 to 30 watts. The 18-volt output is isolated and floating without connection to mains earth. The only earth is at the remote end, so there is no possibility of large mains currents flowing in the event of a neutral fault. The output of the power unit passes through a common mode choke and an LC filter to reduce the 60 kHz switching artifacts on the output, which might affect the remote equipment, particularly the receiver. The 18-volt DC is fed via a twin flexible cable of 0.75 square millimeters cross-section. This is buried about 100 millimeters under a grass lawn by making a slit using a spade and pushing the cable into it. There is no attempt to provide mechanical protection for this cable, as it is in an area that is unlikely to be disturbed, and in any case there is no danger from the LV involved in the event that it is severed. The 18-volt switch mode power supply has full short-circuit protection. The 18-volt supply incoming to the remote location feeds two linear regulated power units. Linear units are used as switching mode power supplies prove too noisy with a sensitive receiver nearby. One PSU produces 5 volts DC at a maximum current of about 600 milliamps. This is fed to the USB hub receiver, and besides powering the USB extender, it then feeds mainly the SDR. A MOSFET high-side switch is connected in the 5-volt power wire in the USB cable to the SDR. This is used to turn the receiver on and off. The other linear power unit produces 12 volts at a maximum current of a little over 1 amp to feed the QDX transceiver and the active antenna. The feed to the active antenna has extra RF filtering to reduce low-frequency noise components from the 7812 regulator chip getting to the active antenna amplifier and marring reception, particularly at VLF. Supply to the active antenna is controlled by another high-side MOSFET switch, which is controlled by what I call the TX command signal from the QDX transceiver, which shows when it is transmitting. The switch turns off the active antenna to reduce the signal level from the transmitter into the SDR. The 12-volt supply going into the QDX passes through two parallel high-side MOSFET switches. The first one, when turned on, is effectively short-circuit and gives the full 12-volt supply voltage to the transceiver. Parallel MOSFET switch, when turned on, passes the DC supply through a string of diodes acting as a voltage dropper. Diodes produce a voltage drop due to the diode forward characteristics, which give a fairly consistent 8.5 volt feed voltage, largely independent of the current drawn by the QDX transceiver. The 18-volt incoming supply is used to power the antenna selection relays via suitable dropping resistors, and the 12-volt supply is used to bias the reflectometer rectifier diode slightly into conduction to improve sensitivity, which is particularly relevant for the reverse wave detector. Telemetry and remote control is provided by an Arduino Uno microcontroller plugged into the USB hub, with which it communicates over a virtual serial link to the PC at the operating position. A Windows Forms app on the PC is used to display measurements and remote control the receiver and transceiver equipment. An interface board plugs on top of the Arduino Uno and carries potential dividers and filtering components to feed into the unit's analog to digital converters. These are configured to use an internal 1.1 volt reference, which defines the full-scale deflection or the maximum range for the ADC measurements. Also mounted on this board is a TMP36 analog temperature sensor, whose output feeds in on one of the ADC channels. This provides remote measurement of the temperature inside the box housing the SDR and linear power units. There are 6 ADC channels available. 2 are used to measure the voltage either side of a 1 ohm current shunt resistor in the 18-volt supply positive lead incoming. From the voltage difference, Ohm's law can be used to measure the total supply current. The output of the QDX power switches is measured, nominally 12 or 8.5 volts depending on whether full or reduced power operation is set. The reflectometer forward and reverse detector outputs are measured to show how well the antenna is matched. These signal pass via calibration potential dividers, which reduce the voltages to be within the 1.1 volt maximum level for the ADC. The 6th channel is wired to the TMP36 temperature sensor mentioned before. Now the digital inputs and outputs of the Arduino. One output line controls the MOSFET switch in the SDR 5V power feed. To confirm the switch has operated, the 5V feed to the SDR is fed into an Arduino digital input. Two outputs control the QDX power switches for full and reduced power operation. The QDX transceiver itself is modified to give a 3-bit status signal which feeds 3 Arduino digital inputs. 2 of these give the band selected by the QDX processor, 80, 40, 30 or 20 meters. The third shows when the QDX is transmitting. This is what I call the TX command signal, and besides feeding into the Arduino, directly controls the MOSFET switch feeding the active antenna. From the band selection data, the Arduino sets one of 3 digital output lines to signal 40, 30 or 20 meter operation to the relay driver board. In the absence of any of these signals being high, the relay board automatically selects the 80 meter relay. Finally, a MOSFET power switch controls power to a cooling fan. This can be turned on remotely, or it can operate in fan auto mode, where it is controlled by the temperature sensed on the Arduino interface board by the TMP36 analog sensor. This is the Windows Forms app used to show the telemetry measurements from the Arduino, and also provides some remote control of my bottom of the garden remote SDR and digital transceiver. The app is written in Visual Basic under the Microsoft Visual Studio 2022 Integrated Development Environment. These 3 boxes show measurements made by the Arduino: total supply current in amps, the voltage supplied to the QDX transceiver when it's on, and the temperature in the box in degrees C. As you can see, it's presently reading 19.9 degrees C. These checkboxes are used as on-off switches. The top one controls the 5V supply to the SDR. This checkbox turns on the QDX with full power and this one at reduced power. This checkbox controls the cooling fan. When under automatic control, the fan switches on when the temperature reaches the set point here. This panel shows what's happening with the QDX. It has virtual LED indicators to show full and reduced power, and another indicator to show when the TX command line is active and it's transmitting. The display here shows what band the QDX is set to, and therefore what antenna is selected. This display is for the reflectometer in the QDX antenna coax line. Forward and reverse voltage levels are shown on the simulated analog meters here, and the actual VSWR calculated is shown numerically here. This checkbox controls a test facility. Any of the parameters telemetered from the Arduino can be checked here. This is the raw data before any processing is done. For example, the 10-bit value of the temperature, 687, is available before any calibration is applied. And if you click on this checkbox, the raw voltages from the reflectometer forward and reverse detectors are shown. So let's turn on the SDR. Click on this checkbox. The virtual LED power indicator comes on. Now I'll start up the SDR software.
Dog in the back of the car with the window open, so he had his head out the window, came through the British Customs, no problems at all, nobody even asked him anything about the dog, got on the ferry, no problem, the dog stayed in the...
That's the SDR working. Now we'll turn on the QDX on full power. The power indicator comes on, and I'll turn off the SDR. To check the QDX is working, we look at the speaker icon here, It shows that the QDX is selected rather than the speakers to the audio system. Now I'll power up the WSJTX software. You'll see that it is set on the default frequency on 30 meters, and the telemetry shows that the antenna selection is indeed set to 30 meters. The QDX supply is showing as 12.1 volts, which is full power operation. I set tune on the WSJTX. The TX indicator comes on and the reflectometer forward and reverse indicators show. The calculated VSWR is shown as 1.5 to 1. Now I can go to reduce power. The power supply drops to just over 8 volts and the reflectometer drops to about a half, meaning it is operating at about 1/4 power, or a little over 1 watt output. Total supply current drops to 0.74 amps. Back to full power, and the current runs at about 0.93 amps and the voltage just over 12 volts as before. Now we can change to, say, 20 meters. There's 20 meters there and 20 meters shown on the antenna selection on the telemetry. Press tune and we get full power shown on the reflectometer. Finally, the fan control is on automatic at the moment. The temperature measures 20 degrees and the set point is 20. I can adjust the set point upwards, say to 21, and you'll see the fan indicator goes off. And as I bring it back down again to, say, 19.9 degrees, the fan comes back on again. There's about a half a degree of hysteresis built into the software. If I turn off the fan auto checkbox, I can then turn the fan on and off directly using this checkbox.